And thanks for the organizers for putting together this very nice conference. So I'm going to talk about taming some coherent errors in the surface code. This will be motivated by quantum error correction, but it's again, a physics talk. So I just focus on the simplest of settings, in particular just code capacity noise models. And my aim is to obtain some statistical mechanics and some phenomenological understanding. But along the way, even from this, we do get some quantitative results, for example, about maximum likelihood thresholds for some of these noise models. So before I would begin, let me thank my collaborators. They did a lot of the heavy lifting in this. Florian Venn, a former PhD student, and especially Jan Behrens, a former postdoc, now at Quantinuum working on quantum error correction. So I'll be looking at coherent errors from a perspective of quantum memory. So suppose you have some code state, the ground state of the surface code Hamiltonian, and it undergoes some unwanted local unitary evolution, for example, a rotation of each of the qubits, and this gives us this error-corrupted state. So in some sense, this is very trivial. This is a local unitary. So for example, the topological order is preserved. But here the question is a little bit different. We want to do syndrome measurements and then ask whether we can recover this initial state, at least approximately, if we do Pauli corrections. And with increasing accuracy as we increase the system size. So why is this tricky? Even for code capacity noise models, at least compared to stochastic Pauli errors. And for that, let me indeed compare the situation to that case. Here, for simplicity, I imagine we start from some stabilizer code state, and then after the stochastic Pauli errors, we get this error-corrupted state, which is then encoded, the information is encoded in this probability density, or probability distribution. This probability distribution is a sum of sub-probabilities, probabilities of error strings that give you the same syndrome and logical label. And because of this, you can always think about these probabilities as some kind of a statistical mechanics partition function with positive Boltzmann weights. Now for coherent errors, the state that we have, the error-corrupted state, is a coherent superposition of these states. So now the information we need is encoded in these complex amplitudes. These are again sums of sub-amplitudes, the amplitudes that give rise to the same syndrome and logical label. So you can, in principle, and we will cast it into the form of a partition function, but if you want to think about the statistical mechanics of that, you will have some complex coupling, so that will be a bit elusive. And there is another point. We will want to know the probability with which one of these states appears, and that's the mod square of this amplitude. And since this amplitude has these sub-amplitudes, this mod square will involve the quantum interference of errors. And so just to highlight, this interference is in principle there even after syndrome measurements. So it's not killed by syndrome measurements a priori. All right, so this is kind of a broad picture that I would like to convey. It is a view on this error-corrupted state and modeling this quantum error correction through quantum circuits and entanglement phases. So it goes like this. You have the probability in the incoherent case or the amplitude in the coherent case. And as I alluded to it, you can cast it into a classical partition function. If you started with a d-dimensional local code, then you will get a d-dimensional local classical quote-unquote StatMech model, where again the quotes are there because for coherent errors, the couplings you have can be complex. So maybe in that case, you want to think about it as some kind of discrete path integral for this quantum amplitude. And then you have this partition function. You can express it in terms of a transfer matrix. What that then gives you is a quantum circuit describing the dynamics of a system a dimension lower. And then from there, we can link back to quantum error correction to see when it can work, when it cannot, so to the phases of QEC by looking at the properties of the circuit's long-time state. So what we learned based on the surface code is that if this state has some non-trivial area law, say it displays spontaneous symmetry breaking, on a surface code you can also formulate it in terms of topological order. This is when quantum error correction succeeds. So this is the QEC phase. But we also find that the nature of errors, coherent or incoherent, can lead to interesting distinctions in the non-correcting phase. So in the bit flip case that I'm going to discuss, you can have some trivial area law, but in the coherent case, it seems that we can have some logarithmic entanglement phase in terms of this picture, so some kind of a quasi-long-range order. And I should mention that in all this, of course, we are building on important work by others, in particular Bravi et al., who described approximate maximum likelihood decoding of the surface code with depolarizing noise using matrix product states, or Peter Liu and Tarun Grover, who discussed this relation between transfer matrix, quantum circuit, and entanglement phases. So I'm going to describe these ideas focusing on surface code, starting with this specific noise model, and I'm going to compare it with its incoherent counterpart, the bit flip channel. So here the StatMech model is a random bondizing model, which can be then expressed, the partition function, as a hybrid free Fermion quantum circuit. And in this case, there is an extra step we can include in this diagram, and it's a two-dimensional scattering network model. It's kind of a cartoon for a disordered superconductor. I find it nice for two reasons. First, it gives to the quantum error correcting phase and the non-correcting phase some nice phenomenological picture. But I hope I won't forget to mention, it also allows you to cleanly identify the maximum likelihood threshold for this noise model. So in this case, the threshold will correspond to a delocalization of this network, and this difference between the phases we can have between coherent and incoherent cases manifests itself as there being, it seems to be a metal above the threshold. And here I should also highlight very important previous work that we build on. First, of course, the paper of Dennis Kitaev, Landa, and Preskill on the surface code with bit flips and its mapping to the random bondizing model. But also for the random bondizing context, some very important work actually from here in Santa Barbara by Matthew Fisher and by Andreas Ludwig, mapping it to this quantum circuit and network models. And especially important for the details of how we understood things are the works by John Chalker with his student Florian Merz, which was really important guidance for us. And I should also highlight another thing that kind of motivated us to get going is this link between network models and entanglement phases, again, by Andreas Ludwig and collaborators. And I hope I have time in the end also to go beyond these two limiting cases that I showed and to study the most general single qubit X error channel that we can have with both coherent and incoherent components. There are several interesting features for this model. For example, the coherent and incoherent bit flip limits, which are free fermionic, are connected now by an interacting phase, and this above threshold metal that I mentioned turns out to be unstable if you include some incoherent noise component. And another interesting thing is how you can capture the phenomenology of this. And I think that's the only thing I'll try to somehow convey in a very high level way, and how it links back to this Ising picture that we had. So the rest of the talk's going like this. I'll be just very briefly setting up a problem in terms of a quantity that we want to focus on, and then I just walk through this diagram of mappings, trying to give the gist of each of the stops there, and time permitting, then I'll talk about the general X errors and the phenomenological model that we'll have there. All right, so I'm going to focus, as I said, on the simplest of settings, just with a single logical qubit. Concretely, I'm imagining a surface code on a cylinder with a logical X along the cylinder. Now, being motivated by quantum error correction, I'm going to focus on features of this error-corrupted state that survive the syndrome measurement. Concretely, these are these kind of quantities, some syndrome-weighted functions of the post-syndrome measurement density matrix. And now we can set up the quantum error correction problem also in terms of such a quantity. And for this, we have to remember what is it that we're asking. So given S, after syndrome measurement, can we do Pauli correction? And to answer that, we have to know, first of all, whether we should correct with CS, which is some arbitrary reference string consistent with the syndrome S, or with CS times the logical X, which is the only other possibility with X errors and a single logical qubit. And the quantum error correction will work if there is a nearly unique answer emerging. When I say nearly, I mean it becomes unique as you increase the system size. And this quantity, with the same structure as this, probes this. So here you have this maximal conditional, and this probes the deviation of that from unity. Yeah? And the quantum error correction phase will require this delta to decay exponentially with the code distance, which is this L here. Okay, so now I'm going to try to set up an Ising model for this quantity. And for that, it will be useful for me to take the code state to be a logical Z eigenstate. I'll be focusing on a coherent case. And this will be just a generalization of the Dennis et al. Approach, although I'll do things a little bit differently. So if it's a logical Z eigenstate, then this set of states is an orthogonal basis in the space accessible by X errors. And we would like to have some StatMech for the corresponding quantum amplitudes. And for that, we are going to inspect this, thinking about expanding this product for this coherent error. The main step is to think about the coefficient of some Pauli X string in this expansion, and we can write it in this funny way that will very quickly get to an Ising model. Here the main ingredient is this indicator function. So if qubit j is in the support of this x, then this is -1. So what this does, then it cancels this cosine and leaves us with the I sine phi. And that's exactly what we should have. And when j is not in the support, then it will leave us with the cosine similar. Okay, so this encodes this expansion, the expansion coefficients. And then the amplitude that we are after will be just the sum of these coefficients for the strings that give us the same S and Q, so syndrome and logical label. So we have such a string, oops. We have such a string, of course, this guy. But any other string that we get from this, multiplying it with an X stabilizer, will also give us the same S and Q. So we have to sum over all these dressings with X stabilizers. We need only X stabilizers because we have an X error channel. These are the only things that can be generated by this. And so what we have then is a binary sum, right, of these kind of coefficients. So the rest of the work is just to manipulate this indicator function with this as an argument, and we have an Ising model. It's a binary sum, so it's already like an Ising. So I'm not going to go through all the manipulations, I just show you the model, but I think the ingredients, the relation of the ingredients to this expression will be apparent. So that's the Ising model. I'm going to flip back and forth a little bit between the slides. So here is this Boltzmann factor, for example, that clearly comes from here. And then the Hamiltonian comes from massaging this indicator function. Remember, here we're summing over X stabilizers. So indeed, our X stabilizers become our Ising spins. That's what we are summing over. And the qubits of the original system are where bonds are. And this reference string, it gives you some bond signs. Okay. So in this way, we have this Ising model for these kind of quantities. And in evaluating this sum, we are effectively sampling from the syndromes, right? And the syndromes enter this Ising model through these bond signs. So in this way, this is a random bond Ising model. Another important feature is that these probabilities, which are related in this coherent case to the mod square of this amplitude, they come from the Ising model. So the disorder and the thermodynamics are interlinked in the same way as it is, as they are on the Nishimori line. So we have some kind of a generalized Nishimori condition here. And let me bring up again this order parameter that we introduced to highlight that through this conditional, it features a disorder correlator. So it's a ratio of partition functions with and without a seam of flip bonds. And this disorder correlator, this is something very well studied in the Ising context, except that for coherent errors, these Boltzmann weights are complex. So in that case, how this disorder correlator behaves and how to think of it is less clear. So that's the motivation to start mapping further to get ourselves to some more familiar ground. This brings me to this next stop, this quantum circuit. So the quantum circuit we get from the transfer matrix, which I believe everybody knows is just a way to evaluate this partition function slice by slice, say going from left to right, and that turns the sum in, so each slice will become a layer in a circuit, and it turns the sum in the partition function in the contraction of a quantum circuit. That's what I call transfer matrix in this talk, this entire object. And this acts on some, it has some initial and final state depending on the boundary conditions of the system. So the steps here that we would have to follow are again completely the same for the bit flip and for a coherent case. So I'm not going to through the details of the step, but rather highlight the differences that we get. So for bit flips we have a more standard random bondizing model. So this quantum circuit that comes from the transfer matrix expresses essentially imaginary time evolution as you would expect from the classical quantum duality. The interesting thing with coherent errors is that the corresponding circuit now has real and imaginary time evolutions alternating. So this is unitary, this is imaginary time evolution. So I think it's a very nice feature because such hybrid quantum circuits played an important role in the field of entanglement transitions and monitored quantum circuits. Here they come out of the box, so that's quite nice. But I have to now come back to interpreting this disorder correlator, and for that, first let us remember that we are interested in the large system size behavior, so when this L is large, and that can be conveniently studied through a singular value decomposition. So here I'm following very closely these ideas from Metz and Choker. The singular value decomposition of this transfer matrix, this large L long times, is dominated by the circuit's long time state, which we can also interpret as the ground state of a Hamiltonian we can associate this MM dagger. Okay. So now I'm coming back to this disorder correlator that we had. Remember that features a seam of flip bonds here in terms of the Ising model. And remembering that this is a time coordinate, that means that at each and every instance of time, we have a transversal coupling whose sign we switch. So from a 1D perspective, we are comparing dynamics with periodic versus antiperiodic boundary conditions. So this disorder correlator probes the dynamics and this 1D state in terms of twisting boundary condition. Okay, and that is something that we can relate to some familiar ideas. So I'm talking about this H here, and I'm conveniently suppressing some indices there to just convey the main point. So when this H is gapped, then twisting these boundary conditions probes the presence or absence of symmetry breaking. The system has some Z2 symmetry, so here I'm talking about Z2 symmetry breaking. Or in a fermion language, this being an Ising model, we can convert to free fermions. We are probing the 1D fermion topology. So concretely what we have is when this 1D system displays symmetry breaking, or the fermionic version of it has topological order, then this suitably defined minimal disorder correlator decays exponentially with L at a rate set by the gap of the system. And using this now in this quantum error correction order parameter, that points out that we are in the quantum error correcting phase. Conversely, when the system is disordered, then this ratio is constant and so is this delta, so that's when quantum error correction fails. So I think this makes some nice connection between this transfer matrix and quantum circuits and symmetry breaking and quantum error correction. It's a conceptual connection, but to make progress with it, we have to now work harder. And for this Ising case, a nice way to work harder is to go to this network model. Again, first, to acknowledge the important works by Matthew Fisher and Andreas Ludwig. The steps to achieve the network model follow exactly the steps they did, and I should especially emphasize John Choker. So again, I'm going to just highlight the differences. And the differences come really from the differences in the circuit that we have. Okay. Actually, I just realized it's a kind of a quantum error correction conference of what is a network model in the first place. So what we have the Ising bonds, or the qubits of our system. Here they take the role of some scattering centers that scatter some incoming mode that they can reflect or they can transmit. Okay. And so the differences that we have in this quantum circuit turn into changing the structure in which we have that we have in this network. So if you see here we have some right transmitting mode or some vertically transmitting modes instead of some reflecting and transmitting modes. Okay, so we have a different structure. So that's one important difference. And there is a common feature, and that's how disorder enters. This is a disorder network model, and the disorder comes from the syndrome distribution. So here we have some plaquettes where we have the Z stabilizers, and you have a vortex there when you have a non-trivial stabilizer eigenvalue. What vortex means in this context is that if a mode goes around such a plaquette, it picks up a pi phase. Okay. But now thinking about the distribution, which is a very important thing in these networks model, it's really subtle. The distribution of the vortices can change the qualitative physics dramatically. That's very different. So in the bit flip case, this vortex distribution, which ultimately comes from the distribution of bond signs, you can just sample directly from your error model, probability P for flipping a bond. In the coherent error case, you had some ground state, you acted with the unitary on it, and then you measure syndromes. So it comes from the bond rule. So that's a very big difference. The good thing is, building on important work by Beri et al., that also in this coherent case, you can sample these syndromes efficiently. And then we later, for more general error models, also developed some methods to do this. So it's something that we can study on the computer. And just to keep also the conceptual link between quantum error correction and now the network model, we also need some kind of a dictionary using the 1D system that we already established the link with as an intermediate step. So here the central quantity is a scattering matrix. This tells you about transport along the cylinder in this system, at least in the geometry, two-terminal transport. And you can use it to obtain the conductivity in particular. And so the dictionary goes like this. If this 2D network is an insulator, so it has some length scale, then the 1D fermions that I mentioned before, they are gapped, and their gap is set by the localization length of the system. In this case, this transfer matrix space, long-time state, has an area law. And we can also introduce a topological invariant for the network that equals the topological invariant you would have for 1D. Just to highlight here that this indeed probes the effect of twisting boundary conditions. Okay. And so in this way, we can link the network directly to quantum error correction. If you have a topologically non-trivial insulator, this is when quantum error correction works. And if the insulator is trivial, then it fails. Now, in the incoherent case, the Ising model has positive Boltzmann weight. So I quote now another important paper by Andreas Ludwig. In this case, only insulators are possible. But with coherent errors, we have complex Boltzmann weights. So in principle, we can also have a Meyer on a metal that has this logarithmically increasing conductivity. And the 1D side, it corresponds to some logarithmic entanglement phase. So it's like a critical system in terms of this error correction order parameter. We expect something like quasi-long range order, some power law behavior. So this is a landscape of possibilities. Let's see what the numerics gave us. So here are the results for this kind of error model. We find that there is some critical angle below which we indeed find a topologically non-trivial insulator. And in terms of delta, that corresponds to indeed the error correcting phase. The numerics also bears this out. And above this angle, it seems that we have a Meyer on a metal. I'm wording this carefully because this may well not be the last word on this. Sagar has some ongoing work. We are also thinking about this. But for the purposes of this talk, let me call it a metal and just say that if it is a metal, that's certainly a different metal than what you would naively think about for this kind of disorder, superconductors. Okay, that's because it has this very intricate disorder distribution. And the critical angle that separates these two phases, so where you have this Majorana delocalization, is the maximum likelihood threshold for this error model. And that's the numerical value that we find. Maybe it's good to put that a bit in a context. And for that, it's useful to consider this Pauli value that you would have if it was not a coherent error, but a kind of a bit flip channel. So that's 0.18. It's quite a bit higher than the maximum likelihood threshold you would get for a bit flip channel. So in this sense, this coherent error threshold is remarkably high, meaning that there is a lot of headroom for some practical decoders to operate. So in the last part of the talk, I'll talk about these general X errors and the phenomenological picture. How much time do I have? That's excellent. Thanks. Okay. So yeah, this is this most general single qubit error channel, coherent and incoherent components. There will be a lot of disclaimers that I'll be doing hand waving here. So before doing that, let me just say that we can develop, and we have developed, a stat mech mapping and with this quantum circuit analysis, and we established this phase diagram, where this marks the maximum likelihood threshold, which you can estimate through entanglement transitions. And an interesting feature that we find is that this critical phase that I mentioned, above threshold critical phase in the coherence limit, that's unstable to an incoherent noise component. So here the entanglement transitions are all area law to area law. So in the rest of the talk, I'm trying to somehow obtain some phenomenological theory, initially motivated by two things. First, to explain this instability, but also to relate the error field double that Yimu and Ehud and collaborators developed, which is a 1+1D theory, to this Ising quantum circuit, which is also a 1+1D theory. So therefore, I'm allowing myself the liberty to do a lot of hand waving in favor of extracting some structural features. So yeah, that's the disclaimer, okay? So what I'm trying to have is some broad phenomenological theory capturing the typical, so suitably ensemble averaged partition function and the correlation functions that we would have for quantum error correction. As I say, the approach is this error field double. So, and we'll see how it gets simplified for these X errors. So we start with this code state, this topologically ordered ground state, and the error field double is simply the action of the error channel on this code state vectorized. But then the nice ideas come in, or even nicer ideas come in, if you start thinking about this state. Now it has a cat and a brass vector that's coming from some imaginary time evolution from a distant past, with the error channel then enacting some extra evolution in the final time slice. So I'm trying to interpret the problem in this picture for X error channels. In this case, it's useful to think about this imaginary time evolution as starting from its all zeros, like here, time flows upwards. And what it does is then implements this syndrome projection, okay, to get the code state. This all zeros is already a +1 eigenstate to the Z stabilizers and the logical Z, so that's all the projection that we need. And I'm going to motivate the structures by thinking about the fidelity. Okay. Now using this form here and that the error channel involves only X's, we can commute this projection through the error channel to get this kind of form, this expectation between the all zeros. So in terms of this space-time box, now we have also a boundary state here that's all zeros. Okay. But just let me remind you of my disclaimer. I'm not doing any derivation here. Okay. Not even for the fidelity. I'm trying to just pick out some phenomenological and structural ingredients. And for that, I'm going to try to somehow get some mileage out of this boundary state here. And for that, let's remind ourselves that the Z in the surface code, it creates a pair of E anions, at least that's my convention. And this all zero state at the same time is invariant under Z. So it condenses these E anions. The error channel, on the other hand, has this axis that creates pairs of M anions. Okay. And one thing that I am involving in this fidelity, thinking that the fidelity and the typical partition functions that we want to consider, they are similar deep in the error correcting phase. Okay? So for this reason, I can involve some phenomenology out of this fidelity. And the fidelity is at its maximal, approaching its maximal value deep in the error correcting phase. And now we have here this boundary state. And to capture this approach to the maximum in a phenomenological theory, then this theory has to have some E-condensation at the boundary. Yeah? And then the error channel competes with this E-condensation through this M anion pairs. And I should always say bar E and bar M anions because we also have this bra sector. And now I'm following Yimu and Ihut further. The next step is to do some space-time rotation. So here, this was time. Now I exchange it with the spatial coordinate, and time now flows this way. So maybe it's useful to look at it from the time direction. So time flows outside of the plane. Okay. So what we have now after this is the dynamics of some topological order, some 1 plus 1D dynamics on the boundary. That's all. That's where the non-trivial things happen, right? It is now that I can invoke some observations from symmetry for topological field theory. This is just a very simple one from the very beginning of the field, okay? And that's the following: these E pair strings and M pair strings that end on this boundary that corresponds to where the error channel was. They have the same algebraic properties as Pauli ZZ and Pauli X on this 1D system, yeah? And now thinking back about the error channel, this is how it looks in double space. And that deep in the error correcting phase, we need E-condensation. The situation is suggestive of some dynamics like this. Yeah? So this term is related to E-condensation. We have this axis corresponding to M pair creation, and we also have this correlated M pair creation. Okay. And so let's see what we can get out of this. For the purposes of the talk, I'll just look at some limits where we know what we should get and see how this at least morally corresponds to it. So first, let's look at the case of no errors. So in terms of this model, it's where G and J are 0, because these are the parts that came from the error model. So in this case, as you remember, we have to have E-condensation. And here are these terms with which you can implement it if we take J to be positive. So this gives you this E-condensing ground state when this stabilizes for +1 eigenvalue, as you should have for E-condensation, or in a dynamical sense, this spontaneous symmetry breaking long time state. So that matches the phenomenology we had from a quantum circuit picture. Now, how about purely coherent errors? That's when this term is absent, because only the incoherent component creates correlations between ket and bra sectors. So in this case, the two sectors decouple indeed. What we have is a transverse field Ising model in an Ising model, an imaginary transverse field. So does it reproduce this log phase that we had for large coherent errors that corresponds to cranking up this coupling? And indeed it does. This imaginary transverse field Ising model has been studied in the field of monitored quantum circuits, and they indeed found a log law for the entanglement. Another limit that we can look at is bit flip errors. So that's when we have no coherent errors, and in this case, the system has some larger symmetry. It commutes with this compound stabilizer, and we can focus on the +1 eigenspace of this object, this being connected to the no error limit. And this allows us to introduce now new Pauli ZZ and X operators, and it reduces the problem to a Hermitian standard transverse field Ising model. Now this J int is what's morally corresponding to the bit flip rate, and this model, cranking the tap, indeed we have an area law to area law transition between symmetry breaking and disordered phase. So this was just to sketch that some known physics is recovered by this admittedly very hand-wavy model, but there are some more things that come out from which we can get some mileage. In particular now, in this large G coherent limit, where it has this log phase, there is something more. This log phase corresponds to a free fermion, or in the bosonized language, a free boson CFT state. And we can use that to develop a perturbation theory in the incoherent noise component in the language of this phenomenological model. And doing that perturbation theory, indeed, in this model also, this log phase is unstable to incoherent noise contribution. So this brings me to the end of my talk. We have seen how for the surface code with X errors, the coherent errors, code capacity threshold can be understood as Majorana delocalization, but also how coherent errors can bring in some new phases in these new many-body systems. This includes this quasi-long range ordered phase, which, however, is unstable to an incoherent noise component. And I hope I could at least give some spotty gist of how this may be captured through this error field double phenomenology. On a larger scale, the surface code investigation suggests that there may be a route to model quantum error correction in topological ordered error corrupted states through quantum surface and entanglement phases. As I said, this was a physics talk looking at just the simplest of settings and code capacity noise models. There is a lot more to be understood. I'll just highlight here some of the points. Thank you.
Right, thanks, Benjamin, for the nice talk. I guess I'll use my powers to ask the first question. So do you sort of expect this behavior to still, well, I guess you did single site coherent noise. If I had like weak correlations in space, would you also sort of expect the same phenomenological behavior?
Actually, Yimu Bao studied an error model like that. And what they found that in that case, you can even have some volume law entanglement in this transfer matrix language. Yeah, you can really have some, I think, new phases. It's an interesting question to look at these coherent errors, but not only as a nuisance, but as a kind of handle you can turn in this many-body system and look for new phases of matter that may emerge.
Thanks. Oh, okay. I guess I'll ask another question. So for the non-local codes, I guess they're, right, like the transfer matrix, you sort of needed this nice like geometric locality to do this.
Yes.
I guess for these more like non-local codes.
Yeah, that's completely open.
Oh, okay.
I don't know what to do about them yet. Yeah.
Okay.
The general question, how do we actually verify that the threshold that we get at the end are correct, in a sense? Is there something to compare to?
You mean like on a quantum computer?
Yeah.
So one thing maybe I didn't emphasize, you can simulate this classically, efficiently, and so you can do this for very large systems. So as to verification, I think that's kind of the best thing you can do, even for bit flip errors, where the threshold is ultimately a numerical question that you look at with classical computers. Mm-hmm. Now, of course, I would be absolutely thrilled to see somebody trying to look at these phases in a quantum computer and to see whether we indeed have a metal or not. One thing that makes that tricky is that in a quantum computer we will have some incoherent noise component. So inevitably you will, I think, at least at large enough system sizes, start to see some area law. And then you would have to work hard. Is it because of the incoherent noise in your system, or is it because it's not a metal? But yeah, I would be absolutely excited for verification.
So you were looking, specifically at X errors, and what if I wanted to have, maybe some unitary error, maybe it's an X rotation only, but also like incoherent X and Z errors. Is there a technical additional complexity that arises in that cases, or does the basic method work? It's just you haven't looked at those yet.
With the X errors, the nice thing is that you can map it to this Ising model. But for more general local errors, you can again develop StatMap mappings, as we have done, for example, for general single qubit rotations. These will be some interacting Ising models. But this broader picture, these transfer matrix entanglement phases, I think that works.
And they're still sort of tractable, at least numerically.
Okay, so one important thing, what makes this tractable, is that the error correcting phase, I think on general grounds, I would expect based on this to correspond to area law with spontaneous symmetry breaking. So what you can do is to use this technique to, firstly, to approximately sample syndromes. I think that's a very important point to emphasize, that you can sample the syndromes, and based on the entanglement phases to at least lower bound the threshold.
Okay, there's no further questions. Let's thank Benjamin again.